We have a shell and tube heat exchanger that has 20 tubes, and each of the tubes undergo 2 passes through the shell. And there is 1 shell pass for the fluid on the shell side. So here's our typical shell, and we're going to have an end. Let me just put an end on it like this, and an inlet end, and this is divided, and we're going to bring some fluid in. All right. The hot water comes in, so I'll just color code it red. Then it goes into how many tubes? 20 tubes, and number of tubes is 20. Then it comes out and goes through 20 tubes out and collected and goes out. Okay. There's 2 passes through the shell. The first pass and then the second pass through the shell. It really doesn't specify if there's a U-turn here or if it just mixes as I've shown it. There's no distinction. All right. And the fluid on the shell comes in here and is going to go out there. So it really only goes through 1 pass of the shell. Yes, there's some baffles to promote the flow going back and forth across the tubes. Like that. So the flow goes back and forth on the shell side across the tubes. The length of each pass is 4 meters. The tube has a 15 millimeter inner and an 18 millimeter outer diameter, and hot water at 0.4 kilograms per second. So the mass flow rate of the hot, which is water, is flowing at 0.40 kilograms per second in tube entering at 77. So it's flowing in the tubes, and it enters temperature hot in. Let me try and sketch this. Temperature hot in is 77 degrees C, and exits the temperature hot out is 37 degrees C. Oil is our cooler fluid. It flows in the shell side. The temperature cold in is 7 degrees C, and the temperature cold out is 37 degrees C. Calculate the convection coefficient for the tube outer surface. So first questions first, what symbol and what expected units for my answer? So we want to calculate an H, but it's on the tube outer surface, so any subscripts on that H? HO. And typical unit? True? Okay. Now, it's going to be a long route to get H naught, but it's embedded in the overall heat transfer coefficient U. And so we recall the equation 1 over the overall heat transfer coefficient is equal to 1 over the H on the inside, area inside, plus 1 over the H outside, area outside. And as long as that area matches U, a lot of times we don't put II on U and A or OO on U and A. We just match it as UA. That equation makes sense? So we can take into account the slightly larger outer diameter than the slightly smaller inner diameter of the tube. Okay. So if you want to calculate the convection coefficient on the outer surface, I would calculate UA and H in the inner surface. The areas on the inner surface, those are pretty straightforward, true? This would be the pi d on the inner, 2 L's because there's back and forth, and that's the area for 1 tube. And how many tubes do we have? 20. Would that give me the total area inner? And likewise, what about the total area outer? Pi d outer, 2L. Why 2L? Each tube has 2 passes. And then why n sub t? Why the number of tubes? because there's 20 of them. Make sense? All right. Now, let's attack H inner first. How am I going to calculate the convection coefficient on the inside of the tube? It's forced convection, so we're probably going to check the Reynolds number to see if it's laminar or turbulent. If it's over 2300, turbulent. I'll look for a Nusselt correlation. The name of the most popular, easiest one, especially on exams in this semester, would be the Dietz-Bolter. That will give me the Nusselt number. Once I have the Nusselt number on the inside, I get the H on the inside. True? So, in order to get it, I need to get fluid properties. So, what is the temperature average that I use to evaluate for the water? Because the water fluid properties are temperature dependent. It'll be the 77 in 37, add those two together, and divide by 2. That'll be 57 degrees C. And when I look in the table, they have it in Kelvin, so I add 273, it's 330 Kelvin, and it's a line in the table, and I'm so thankful. Because if it's a line in the table, do I need to interpolate? No. So I could just read off the properties. What properties are going to be needed to calculate that Reynolds number for flow inside of one tube? You can give me two favorite equations to calculate Reynolds number for flow inside a tube. Rho V D over mu, or true? Now, somebody says, I know the diameter inside, that's easy. That was 15 millimeters, 0.015 meter. I need to get the viscosity of the water at 330 Kelvin, 489 times 10 to the minus 6 units of Newton second per meter squared. And the mass flow rate, I have to think about this a little bit. Is it the mass flow rate of the water? They give it to me as 0.4 kilograms per second. But is that through each tube or just coming into the heat exchanger and then passing through and separating and going into 20 different tubes? Each. It's a total mass flow rate. The water flow at 0.4 kilograms per second flows inside the tubes, but it enters at 77. But it's not, I know that it could be interpreted either way, but it's the total flow for all of them. So the m dot's going to be 0.40 kilograms per second divided by the number of tubes, and there's 20 tubes. So you divide by 20. 0.02 kilograms per second. And when you calculate the Reynolds number, we calculate a Reynolds number which is 3,472. How do I interpret that Reynolds number? Barely turbulent, but turbulent nonetheless. Okay. You could check the entrance region. How long will it have to go before it's fully developed inside each of those tubes? Rule of thumb. How long? It's turbulent flow. 10 Ds, 10 diameters. So the length for entrance is around 10 diameters. A diameter is 0.015, so it's a 0.15 meter length to be fully developed. It's 4 meters long. I'm going to neglect the entrance length. It's fully developed the whole length. True? So we calculate the Nusselt number, 0.023, Reynolds to the 0.8, Prandtl to either the 0.4 or 0.3. You look at the correlation, it's 0.3 when the fluid inside the tube is being cooled, not heated. The hot water is being cooled as it flows through the tubes. So we use a Dietz-Bolter correlation. We calculate a Nusselt number, which is 22.1. The convection coefficient on the inside, Nusselt times K divided by D. You have to go back and get the thermal conductivity of water at 330 Kelvin. and you get the H is 956 watts per meter squared degree C. A lot of work to get H in her. So we finally got this term calculated. We're looking to calculate H naught. Everything in this equation I know except for UA. How am I going to calculate UA? Yeah, let's go ahead and use the effectiveness eNTU method. So I'm going to have to make some more room here. I'm sorry. I'm just going to have to add another sheet, okay? So what I need to do is I need to find UA. To find UA, the pattern is the number of transfer units is UA over C min. Hence, if I could get the number of transfer units, then UA is equal to number of transfer units times C min, right? All right, how do I find the number of transfer units? Well, I'm going to look for a function of effectiveness and the ratio of heat capacity rates. Well, I'll have to calculate the heat capacity rate of the cold fluid. The heat capacity rate of cold fluid is mass flow rate of the cold times specific heat of cold. And that comes in at 2231 watts per degree C. Heat capacity rate of the hot fluid is the mass flow rate of the hot fluid times specific heat of the hot fluid. Let me go back to my problem. The hot fluid was the water. I needed to get the specific heat at 330 Kelvin. What about the oil? I skipped that a little bit, didn't I? For the oil, you calculate the average temperature is the temperature coming in of 7 plus the 37 divided by 2. It comes in average of 22 degrees C, which is 295 Kelvin. And so we get the fluid properties for oil at that 295. So we can get for the oil the density, the specific heat, we can get viscosity, thermal conductivity, Prandtl number, whatever properties we want. All right. So that was for the cold fluid to give us the heat capacity rate of the oil is 2231. The heat capacity rate of the hot fluid 1674. So C sub R, the ratio is 0.75. All right, so we have this part. I need to get the effectiveness. The effectiveness is the actual Q divided by Q maximum. What is my actual Q? The actual Q is known from it's 66,944 watts. And the Q max is C min times temperature hot in minus temperature cold in. And that came in 152 watts. Hence the effectiveness we back calculate to be 57%. So we have now the effectiveness. Well, I have to go and I have to find the right correlation for a heat exchanger like this, where I have 2 tube passes, 1 shell pass. I can do it graphically. So what did we just get? We had about 57% for the effectiveness, so somewhere along this line. And what did we have for the ratio C sub R? 0.75. And so we can read off the number of transfer units, a little less than 1.5, 1.43. No, I didn't do that with 3 digits reading a chart, but you can read a chart and get close. Or you can go to an equation, shell and tube heat exchanger, 1 shell pass with 2, 4, or multiple tube passes. Well, we have 2 tube passes. It's a little step. You have to calculate this parameter E. If you calculate the parameter E, it comes into 1.4. When you calculate it, you put it up into this next equation for the number of transfer units. And there it's 1.4334. Too many digits, but there you go. So that's how you would calculate the number of transfer units. One shell pass, two tube passes. So we calculate this to be 1.4334. That goes into here with the C min. We calculate UA to be 2,399 watts per degree C, or Kelvin. So that's what I needed right here. So now I can go back to the previous slide. 2,400 watts per degree C. So we have 1 over 2,400 watts per Kelvin. You have 1 over H inner, 959. You had all that area inner. 1 over H outer, all that area outer. I'm going to skip over here. I hate to. Let me just give you the number. 7.5398 meters squared. Area on the outside. 9.0478 meters squared. Hence, you calculate from this equation right here, the H naught. H dot 397 watts per meter squared degree C.